How's it going, guys? So another problem, right, for beams. In this one, same thing, displacement, slopes, and nodes, forces in each element, and the reactions. But we will be using symmetry. You have two rollers and two pins on each side. As you can see, right, everything's symmetrical. So what we're gonna do is we're gonna cut down that 80,000 in half, and we're gonna change that node 3 into a roller going down, into a fixed roller, and you'll see what I mean in a second. But then after that, we'll draw the shear and bending, and we'll go from there. So cool, let's get started. All right, guys, so the trick to this problem, we're gonna have to be using symmetry. In this case, right, you have two supports here identical, and then these two are identical. So just cut this in half, cut this in half, right, 4 meters. So you'll have a element that's 3 meters long and an element that's 2 meters long, and this support here gets substituted by a roller. Okay, so this is going to come down some value, right, because at the end of the day these two pieces are attached. So that's kind of the trick to these. This is fixed, and you might think that your boundary conditions in this case is going to be we don't know displacements and we don't know rotations, but because this is going to rotate the same as this is assumed, well, it is 0, right? I mean, if you apply a force here, just think of it logically. If you apply a force going down, this is going to create like a U shape, right? So right at this center of the U shape, you're going to have a slope of 0, right? So these are the boundary conditions right there, okay? So before we do the boundary conditions, my bad, I went too quick. It's the element stiffnesses, right? Because this one, in this case, right, let's stop looking at this for now, I guess. Let's look at this. It's 3 meters and 2 meters, and our stiffness depends on length, right? So that means each of these two elements are going to have different stiffness values or different stiffness matrices. So what we need to do is first calculate EI over L cubed, right, for both elements. In this case, L is the only thing that changes, but it could be I, it could be E, right? You have different materials, different cross sections. In this case, we just have different lengths, 3 and 2. So when you do the math, you get your first stiffness for this element is 2.59, and then for this element, you have 8.75. Okay, so because of the length, it's shorter length, so that means it is a little stiffer. Well, actually by a lot, right? 3 times almost, give or take. So once you calculate these, okay, then we go to the boundary condition. That's kind of what I was saying, right? So in this case, V1, it's fixed in the Y direction, but it could displace. I forget the exact names. Roller and pin, I want to say. I have to double check that, but it doesn't matter. What you need to know is what are the boundary conditions at these nodes, right? So in this case, V1, no matter how much force you put anywhere along the whole beam, that's not going anywhere. But it could rotate. There's nothing preventing it from wanting to rotate. So that means there is some rotation. That's V1, Phi1, okay? So V1 0, because we know it's not moving up or down. Phi1 is questionable. We don't know. V2, this is a roller. It's going to prevent displacement in the Y direction, so V2 is equal to 0. And then there is going to be some rotation. So they're similar, right? The pin and the roller, similar in terms of boundary conditions, okay? They're exactly the same. V3, it's going to come down some value if you apply a force, but remember, the U shape, what I just mentioned, that's going to be 0, okay? So in this case, we know 3, we don't know the other 3. So we could go ahead and start assembling the stiffness matrices, okay? So this is what I did. Hold on. I mean, it might look a little confusing, but let me explain it. Let's go one by one, okay? Let's start with K1. So we're looking at element 1, which is the 3 meters, okay? In this case, we were going to use the same exact template, right? EI over L cubed, which is 2.59 times 10 to the 5th. But you only see 10 to the 5th, but that's because I integrated it into the matrix. So for this element, 31.08, that's 12 times 2.59, okay? If you do that number, if you do that math, you'll get this number. And you just follow the same template for all of them, okay? And it's symmetrical, so in that case, it's right. I hope you're seeing the pattern. All I did was get that 2.59 and I threw it in there. Same for element number 2, right? All I did was get that 8.75 and threw it into the 12, 6L, negative 12, 6L. And we know L, remember, it's just 3 and 2. So it changes for each one. In this case, it was, let's do this element, 6L. This number was 6 times 3 times 2.59, okay? In this case, it was 6 times your length, 2 times 8.75. So the reason you have to do this is because you cannot make the global stiffness matrix unless these outside numbers, in this case 10 to the 5th and 10 to the 5th, match. It used to be 2.59 times 10 to the 5th and 8.75 times 10 to the 5th. You cannot add them together, right? It's kind of like, I'm just gonna go ahead and write it right here. It's kind of like, imagine you had 5 times 3 times 2, okay? And imagine on this side you had 6 times 3 times, let's do 2 again. Well, you cannot add, you cannot do, I guess what I'm trying to say is, you got to get the common denominator out. In this case, it's 10 to the 5th in order to add them, right? So in this case, if we could pull out a 3, we'll have times 10, right? And in this case, we'll do 3 times that, right? I just factored out 3 on all of them. And now I could add these 2 up, right? Assuming I had to add both of these numbers. That means this one's 30, this one's 36. Well, I mean, I'm sorry, hold on. This would have been, let me cross that out. This would have been the same as 3, 10 plus 12, right? That's exactly what I'm doing here, okay? I just thought of this on the spot, so if that didn't make sense, I'm sorry, but point is you cannot add these matrices unless these numbers concur, are the same, okay? Just keep that in mind. So now that we have that, we could go ahead and start making the global equation. So let me again start it all over. I already finished it, but this would have been F1y, M1, F2y, M2, F3y, and M3, okay? Equals, in this case, 10 to the 5th, right? And then I'm gonna make my big matrix from nodes 1 to 3, right? 1, 2, 3, 3 nodes. V1, Phi1, V2, Phi2, V3, Phi3, and same going this way. Now, element number 1 goes from 1 to 2, okay? So that means from 1 to 2, and then 1 to 2. So this right here is element number 1, okay? Element number 2 goes from 2 to 3, so I'm gonna get this matrix, and I'm gonna throw it in here. So from 2 to 3, and then from 2 to 3. And it's all of this, right? Now these 4 overlap with both elements, right? Because they both share node 2, so that means V2, Phi2, and V2, Phi2, these 4, they overlap. So it means you just gotta add them, right? So in this case, I added 31.08 plus 105, that gives me this. Minus 46.62 plus 105, that gives me this. That gives me this. Then same with this one, right? These 4 and these 4, they overlap. So that's how I got the matrix, okay? And then the displacement vector, the slopes at each node, V1, Phi1, V2, Phi2, V3, Phi3, okay? Now once I got that set up, now I can start erasing and putting my zeros or my knowns pretty much, right? So in this case, we knew V1, V2, and Phi3, so I plugged that in, boom, okay? Now because I knew it, that means I don't know F1y. Because I don't know Phi1, that means I know M1, okay? So using that knowledge, right, I already have this vector set up. I plugged in my boundary conditions. Cool, no big deal. So we're done here. Now let's go to this side. F1y, do I know it? No, because I know my V1, okay? M1, I don't know Phi1, so that means M1 should be, if I don't know it off the top of the diagram, that means it's gonna be 0, right? And yeah, there's no external moment being applied, so that's 0. F2y, there's a reaction, right? This is fixed, so that means we don't know this. V2, there's gonna be some displacement, so that means there's gonna be some moment. I mean, there's some displacement, so that means we should know moment. That's what I'm trying to say. And in this case, yeah, there's no external moments being applied, so that's 0. We have node 3, right? Oh, I'm sorry, I was referencing the wrong diagram this whole time. Okay, my bad. Forget this. Same thing though. 1, 2, 3. 0, phi1, 0, phi2, phi3, and 0 right here. But in this case, my bad. Let's start it all over real quick. F1y, there's a reaction, so that means there's going to be some force. We don't know what it is. There's 0 moment being induced, so that's 0. F2y, there's a reaction, so that means we don't know it. There's 0 moment being induced, right? There's no counterclockwise or clockwise moment, so it means it's 0. You got minus 40,000, right? It was originally 80, but because of symmetry, you got 40,000. So that's negative 40,000. And work with newtons and meters. So kilonewtons gets converted to thousands, okay, right here. And then M3, there is some moment being applied. Now you might look at it and look at the big picture and think, well, there's nothing going on. The thing is, when you use symmetry, that doesn't necessarily apply anymore, but at the end of the day, you will still have 0 at the end because symmetry accounts for this side, and then you set it equal to this side, but opposite signs. So whatever number moment you get here is going to get counteracted by this moment, if that makes sense at this node. But in this case, there's going to be a moment. We don't know which one it is, so we'll just hold on to it, okay? Now we can start assembling our equations, right? So we're going to have, in this case, focus on the displacements first, phi1, phi2, and v3. So you have 0 is equal to 10 to the 5th, but you divide it by it, so it goes away, right? You're going to have 93.24 phi1 plus 46.62 phi2 plus 0 v3. Then you do the next one. 0 is equal to, let's look at it here, right? 0 is equal to 10 to the 5th, but you just divide by it, it goes away. I'm looking at this one. 46.62 phi1 right here plus 233.24 phi2 right here, sorry, minus 105 v3, okay? I'm just doing basic matrix algebra, nothing crazy. It's just kind of hard to look at it right now. There's a little glare because of the sun. But then this one, negative 40,000 divided by 10 to the 5th will give you negative 0.4. 0 phi1 minus 105 phi2 plus 105 v3. And 3 equations, 3 unknowns. Plug it into your calculator, you'll get these numbers. These numbers have been verified, but let's assume they haven't, right? Let's make sense of it intuitively, right? If you apply a force here, right, let's kind of make sense of it, okay? If you apply a force here at node 3, this is going to make a negative angle with respect to the positive x-axis, right? So phi3 is going to be, oh, in this case, my bad, I'm sorry, phi3, no, 0. V3 is going to be negative if you apply a force going down. And what I said is true, but the reason it doesn't make sense here for phi3 is 0 is because, remember what I said, the opposite's going to counteract it. But generally speaking, if this was our situation, that would have been the case, okay? But in this case, V3 is negative. Does that make sense? Yeah, if you apply a force here, you're going to go down. Phi2 is negative. If you apply a force here, well, you can imagine this curve is going to look something like that, right? It's going to come down, kind of like if you're jumping on a diving board in a swimming pool. So it's going to make a negative angle with respect to the x-axis. So yeah, that negative makes sense. Then phi1, it's saying it's positive. Does that make sense? Yeah, kind of, right? You can imagine your curve is going to look like this. Boom, right? I didn't draw on it, but you can imagine it. And if it doesn't make sense, imagine like 2 people on those playground toys. I forget the exact name, but where pretty much one person sits on one end, the other one sits on the other, and it's counteracted by the little support in the middle. It's kind of the same thing, right? If you push down here, in order for the system to be in equilibrium, this also has to come push down. So F1, we anticipate it to be a negative force, okay? And F2, a positive force. And whatever these 2 numbers are, the forces, add them, and they should equal 40,000 going up, okay? A positive 40,000 going up. So let's see if that's true. Now that we have these numbers, we could go ahead and find F1y, F2y, and M3. And when you do that, it's the same thing, right? We're gonna go ahead and do this. F1y is equal to 10 to the 5th plus 46.62 phi1 plus 46.62 phi2 plus 0 v3, okay? So F1y, when you do the math, plug in your phi1 and phi2, you're gonna have F1y is equal to 8,900 going down. So yeah, that's what we anticipated, right? Pushing down. F2y is 10 to the 5th minus 46.62 phi1 plus 58. I'm sorry, give me F2y. Is this correct? F2y is equal to 10 to the 5th. Oh yeah, this is 58.38. Phi2 minus 105 V3. Okay. When you do the math, you have 48,900 going up. Now, does that make sense? I told you, yeah, right? This is pushing up while these two are pushing down. And then the sum of these two have to equal 40,000, but in the opposite direction. And yeah, look, F2y and F1y, you get 40,000 even. Now, these are rounded numbers, but even then, they're very close. You'll see once you actually do the math. Then M3 equals 10 to the 5th, 70 phi2, right? Because 0 phi1, 70 phi2, and then 105 v3. Once you do that math, you get 53,347. So yeah, I mean, that's the reactions and then the displacement vector. But now that we have that, we could go ahead and find the element forces. So let's do element number 1. It's between nodes 1 and 2, and it's 3 meters long. And we're going to use this stiffness matrix to do that, okay? So in this case, you do F1y, M1, F2y, M2, right? Between nodes 1 and 2 is equal to the stiffness. That stiffness was 2.59 of element 1. And then times that K matrix that I just told you about, times your displacement vector, V1, phi1, V2, phi2. I just plugged in these numbers from the solutions that we got here, and obviously the ones I knew. So once you do that, same process, F1y is equal to 2.59 times, this is 0, 6L times that will give you this, minus 12 times 0, 6L times phi2 will give you that. Do the same for all of them, and you'll get these numbers, right? F1y, boom, boom, boom. Plug in the numbers, you get negative 8,900. M1, F2y, and M2. Just keep doing what I was doing, right? Multiply, boom, boom, boom. Just keep it going for all 4 of them. That'll give you the forces in each element. Okay, now you can't verify them yet. You got to get all your elements. In this case, we have 2 elements, right? So that means we got to do it one more time, and then we can verify them. So F2y, same thing. You get the stiffness, 8.75 times 10 to the 5th. And then you use the K matrix, right? Just the template that I told you guys at the beginning of the page, right here. And then your displacement vector. This one is V2 phi2, V3 phi3, because you're going from nodes 2 to 3, okay? Now, it's important the direction you choose, right? Technically, if you were going to go this way, you would have done 3 to 2. So it would have been V3 phi3, V2 phi2. So you got to just keep that in mind. But in this case, nothing crazy. I got to get that out. I don't know what that is. But do the same thing, right? 8.75 times, open parentheses, 12 times 0, 6L times that, minus 12 times that, 6L times 0. And that's what you get. Do the same for all of them. M2 is equal to this number, 6LV2, 4L squared phi2, minus 6LV3, 2L squared phi3. And we know L, remember. We know L in both cases, so we know everything on this side of the equation. This is what we're looking for. So that's what you get once you find that, okay? Now, let's verify the answers. To verify these, if you've been following my videos, you know how to already, but you just add them up, and whatever you add up has to equal the big one, if that makes sense. So we'll check it out, look. In this case, add up all your F1Ys. Let's do the first one, F1Y. Add up all the F1Ys that you see. We have 1, 8,900, right, negative. No. So in this case, we only have 1, and it's negative 8,900. So this F1Y, the little one, little f, should be equal to my big F1Y. Is that true? Yeah. Negative 8,900. Let's do the same for M1. In this case, we only have 1, right? Out of these 8, only one of them is M1, and it's 0. Does that match your big M1? Yeah, it does. 0, remember? Let's do F2Y and M2. F2Y is 8,900 here, and then you have another one, 40,000. So together, it's 48,900. Does that make sense? Yeah, F2Y is 48,900. And then just do M2 real quick. Well, in this case, only the element number 2, right? I mean, node number 2 gets shared. So you'll have an F2Y M2 and then an F2Y M2. And then these should equal your big F3 and M3. But look at M2. This M2 plus this M2 will give you 0, right? And is that the case here? Yes, it is. Boom, so it's 0. So these numbers are verified. Boom, we are done. Forces in each element, we're good. Now the elements, remember it's symmetrical, right? So this problem had an extra step, it's symmetrical. So forget about these diagrams for now, right? Just look at these two. Elements 3 and 4. So elements 3 and 4, they'll share the same F1s, F2s, F3s, whatever, all the forces. The M's just switch signs, okay? So F1Y, right? Remember element 1, 2, 3, 4, okay? In this case, we had just 1 and 2 here, but 1, 2, 3, 4. This one got broken up into 2, okay? So this forces in each element is going to equal to this one. So element 1 should equal element 4. Did I put a 5 here? Why did I put a 5? Oh, I'm sorry, that's just the F5Y. Yeah, same thing then. This is element number 4 here and element number 3, okay? So in this case, element 4 is equal to the nodes between 4 and 5, right? And I just got these numbers and did the same thing here, okay? Now the M's, they become negative. So this M is a negative M5. It is just 0. This M2 became a negative M4 on the opposite side, right? And it's negative 26,000. Is that right? Am I looking at the right one? F2Y equals F4Y, 8,900. And then M2Y. Hold on, let's keep it going for now. I'm a little confused because look, 2,600. All right, there we go. So my bad, I had a slight issue, but I just messed up some signs here. Like that should have been a positive. But here's what happens. And the reason I was able to verify is by looking at this moment diagram. So thankfully I had it. But we found these, right? So, and I labeled them element number 1, element number 2, element number 3, and number 4, right? 1, 2, 3, 4, those are my elements, right? 1, 2, 3, 4. So in this case, we found element number 1, element number 2, and then element number 3. So what happens is the moment signs switch, okay? So in this case, element number 1 goes from 0 to 26,000 negative, right? Because there's 0 moment being induced, this is a positive 26,000. And you wouldn't have known that unless you did the equations, but it makes sense intuitively, right? Because when you add them up, you get 0 moment for M2, and that makes sense. Now, once you go to M3, in this case, you got positive 53,000. That means you know that the other side of M3, right, element number 3, in this case, this element here has to give you a negative 53,000. But the trick to these is the forces stay the same, but the moments change signs, okay? So 53,000 becomes a negative this way, right? Think about it like one's fighting counterclockwise, but the other one's fighting clockwise. So it could be a million, it could be 2, it could be whatever. As long as they're both equal and opposite, they're going to give you 0, okay? So that's the trick. Your M3 would give you a negative 53,000, but the forces stay the same, okay? And then in this case, once you go to the next one, element number 4 is equal to element number 1, and they change in sign. So M2 becomes positive, 0, 0, and in this case, right, 26,000 became negative, 53,000 became negative. And I'll show you how I verified it once I get to these diagrams. So before we get to the diagrams, you got to just do a quick little summary of what your external forces are, right? So in this case, you have this pushing up. No, I'm sorry, this pushing down. So that means this one's pushing down. You have these two pushing up, and then you have this pushing down. There's 0 moments, right? We don't see any moment. So we got this as our beam, right? 8,900 going down, 8,900 going down, 48,900 going up, and 80,000. Now it makes sense from a static checkpoint, right? Because these two will give you 40,000 going up, and these two will give you 40,000 going up. And you have 80,000 coming down, so that means the system's in equilibrium. Okay, so let's do the shear and bending diagrams. Basing it off this, right? You start off by 0. In this case, you have a point load pushing you down, so you go down 8,900, okay? Nothing happens, nothing happens, nothing happens up until the 3 meter mark, right? And that's where you have 48,900 pushing you up, right? So 48,900 will bring you up to 40,000. Then nothing happens up until that 80,000, right halfway between the beam. That pushes you down 80,000. So you went from positive 40 to negative 40. Then you have, for the next 2 meters, you don't do anything until you get to this 4,900. Pushes you up to positive 8,900. And that positive 8,900 brings you back down at the end, okay? Now, that's the bending diagram. Just shade it in, zeros right here. In this case, well, now what I like to do to get the bending is, that was a shear, my bad, I'm not sure what I said. But to get the bending, all you do is 8,900 times 3 in this case, you get 26,700, but because we're below 0, it becomes a negative, okay? This one is 2 times the height, right? It's just area under the curve. That's all I'm doing. It's just the integral, no big deal. 40,000 times 2 meters, that'll give you 80,000. And since we're above 0, it becomes a positive. Same thing with this one. 2 times negative 40,000 will give you negative 80,000. And this one will give you 3 times 8,900 will give you a positive 26,700. Okay? Now, because the reason I do this is real easy to make the diagrams, right? For the moment diagram, since there's no external moments acting on the system, there's no circular clockwise, counterclockwise. That means everything is based off shear, okay? Those counterclockwise, clockwise push you up and down on the graph. A negative will push you down, okay? I mean, a counterclockwise will push you down. Counterclockwise is usually positive, but when you do the diagrams, it goes down, okay? So I know you might think, oh, it's counterclockwise, I'm gonna go up on the diagram. No, it brings you down. So that's just something to keep aware of. We don't need it in this case, right? We just have point loads, no big deal. So in this case, you start off 0 because there's no external movement, so you start off 0. You go down for the length of 3 meters, you will end up at this value, 26,700. So you're gonna go down at the 3 meter mark, and it's gonna bring you at negative 26,700. And it's negative slope, right? So you're gonna have a negative linear slope. This is nothing more than like y is equal to negative 8,900 in this case. Take the integral, what's negative 8,900x, right? So for every x, or every 1 meter, you're gonna go down negative 8,900 because it's under the 0. So you're gonna go negative 8,900 plus another, you're gonna end up like at negative 17,000. Then you're gonna come here negative 26,700, 3 times. Then for the span of 2 meters, you're gonna go up 40,000 every single time, and it's positive, so we're going up now. So 1 meter, you go 40,000. The other meter, you go up another 40,000, right? Is that what it's doing? 26, yeah, 40,000. That's all it's doing, okay? So we went up 40, then another 40 at the 2 meter. Now you have a negative 80,000, so you're gonna come right back down. So in 1 meter, you're gonna go down 40,000. The other meter, you're gonna go down 40,000. So you end up back at negative 26,700. Then that positive 26,700 along the span of 3 meters, right? So it's gonna bring you back. And that's it. That's the problem. Trying to keep it short and simple. Hopefully that made sense. Hopefully this didn't confuse you. I know I cut off, but sorry, I just knew something was wrong, and yeah, that should have been positive. But at the end of the day, remember, when you do symmetry, the moments, in this case, this was symmetry, right? It was cut at these 2 elements, then these 2 elements were just symmetry. So the forces stay the same, right? Force element number 1 is this one. Element number 4 is this one. So F1y is going to equal to F5y, right? Node 5. And then you just pretty much set this equal here. But the only thing that changes is the moments. They switch signs because they got to counteract each other, right? So that's why you do it. Element number 2 to 3, all the numbers here make sense here. And the moments just switch sign. Positive, negative, and there's negative, positive. So cool. That is the solution. I hope that made sense. I hope you were able to see everything. But yeah.